Okay, welcome back. So now let's consider again the CHD and age data, and we're going to use logistic regression to produce estimates of the coefficients for the logistic regression model. Now I'm going to show you in this course, I'm going to show you, always show you the stat output, but I'm going to show you one additional program in this section because it's actually going to be helpful to us next week when we are learning about how to test for the significance of coefficients in the logistic regression model. And so that's a program called SysStat. And SysStat is actually a program that I used fairly extensively when we wrote the first edition of our book, because I came on sabbatical with what was then a very expensive but a very slow microcomputer. And we didn't really have a lot of software available to do logistic regression on microcomputers, but one that was available was SysStat. And so the way SysStat worked is you would give it some control language first. So here I told it format equal 5, told it that I wanted 5 decimal places of accuracy. And then I told it to run the model. CHD is a dependent variable, equals constant plus age. So that says I want the model, CHD is beta naught plus beta 1 times age. And then I said L options, so I'm asking for some options here, and I'm asking it to give me means, as you'll see. And then when you say estimate and hit return, it goes into its thing and starts to give me the output. So here's the output for binary logistic regression. You can see the dependent variable is CHD. There were 100 observations. The sample splits as follows. You have 57 of the people is what they call referent group. That is the people of y equals 0. And 43 of the people, the respondent group, that is the people with y equals 1. So we have 43% of the individuals in the sample have evidence of CHD. Let's remember that there's 43% of the sample have evidence of CHD. And then you can see that what this option means tells me that the mean age of the individuals who have evidence of CHD is 51.3 years. But the mean evidence of those who don't have CHD is 39.2 years. So you can see, again, that the people who have CHD appear to be older by roughly 12 years than the individuals who don't have CHD. And then it goes on to the exciting part. Remember that when I did this back in our first edition of our book, when computers were very slow, this was very exciting because you would push the button and it would start. This came out almost right away. Minus 69 point something, and then it would sit there for, and have you ever stared at a computer screen for 20, 30, 40 minutes in a row, and you don't know, that's a long time, and you don't know whether or not the computer died altogether, or if it's thinking, or you don't know what it's doing, and then finally it comes up with iteration 2, and so you're so happy that it did that, but then you got to wait another 30, 40 minutes for the next one. So I learned pretty soon that I just sort of would push this button before I went to sleep, and when I woke up in the morning I had the output. And this was, so the end of the day, here's the log likelihood at the 4th iteration, which was the final iteration. So it just repeats that log likelihood. This is just, as it iterates the values of beta, it updates the log likelihood. And notice that the log likelihood is getting bigger and bigger. Okay, it's getting less and less negative, until the biggest it could ever be is minus 53.676. That maximized the log likelihood. And the values of beta that did it were beta naught, which was minus 5.31, and beta 1, which was 0.11. Those are the coefficients that maximize the log likelihood. And so this table is arranged much like the table in a linear regression program. You have the coefficients for the model. Now, of course, the model is a little different here, but these are the coefficients for the model. By the way, I'm going to come back to everything in here later on, but I want to ask a question, and I want you to think about what is the meaning of a probability. When I say that we're going to compute the estimate of the probability for each person in the study, what is that an estimate of? I mean, suppose that I told you that the probability that this person has CHD is 43% or 57% or whatever. What does that mean? And the right answer to what it means is you have to think of it from a population point of view. If the probability of the event is 43%, it means that out of 100 people who have that probability, you expect that 43 of them have evidence of CHD and 57 of them don't. Otherwise, it's not a very good model if anything very different than that occurs. So it's simply saying what it expects to see in a population of 100 people. 43 out of the 100 will have evidence of CHD. Okay, that's the meaning of probability. And we need to keep this in mind. People use probabilities, these models, for all sorts of things. And some of the use of models is, I think, highly suspect. For example, if I told you that, a patient is very sick, and in fact they decide the patient has to go into intensive care. And let's say that I told you that this intensive care unit is a small unit that has one available bed in the intensive care unit. And if I told you that this patient's probability of dying, if they got ICU care, based on a logistic model, is 48% probability of dying. But I told you there was another patient who also is very sick, and this patient's probability of dying is 52%. So I have a 48% probability patient and a 52% probability patient. How do I choose which one gets the bed? It's a difficult question. People make decisions about that all the time. What if I told you that one patient's probability of dying was 3%, and another one's probability of dying is 97%? Who gets the bed? So you may think that, oh, 3% patient's not very sick. But actually, what that says is that if they got ICU care, their probability of dying is only 3%. But if they didn't get ICU care, we have no idea what their probability of dying would be. In any case, a patient whose probability is 97%, we know that even if they get ICU care, they're likely not to do well. And so if it's limited resources, then you might want to give the bed to them. What do you use these models for? I mean, a lot of people simply look to see if the probability is above or below 50%. And it's above 50%, they say, oh, the patient's going to die. Below 50%, they say, oh, the patient's not going to die. Well, that's not kind of fair either, right? Because let's say I have two patients, one whose probability is 51%, another one whose probability is 49%, right? I mean, virtually, if you think about the interpretation of probabilities, there's no difference. But if someone simply compares the probability to 50%, they might think that you're over 50%, I'll predict that you're going to die. Under 50%, I'll predict you're going to live. That's a misuse of the model. Because the model is not making predictions. The model is estimating probabilities. And so turning an estimate into a probability, or an estimate of a probability into a prediction is very problematic. And we're going to talk about that later on in this course as well. Okay. Let's look just quickly at the stat output, and then I think we've done what we want to do for today. This is the stat output, very much the same. To use stata, actually, why don't we do this? Let's take a quick break, and then we come back. I'll actually fire up stata on my computer, and I'll show you how you do this yourself, and because you're going to have to use it in the homework in any case. So let's just take a break now, and we come back, and we'll look at the stata output.